Half, okay, it's half, okay, because it's double. Right, and it's equal to half I1 squared minus half Tij. It can be proved, okay? When you go home, you can check it, okay? And I3 is equal to the determinant of T. That is T11, T12, T13, T21, T22, T23, T31, T32, T33, okay? And it's also equal to 6 EIJK, EPQR, TIP, TJQ, TKR, okay? You can try to check this notation, okay? Yeah. And we call this this is an invariant. So this is a first. This is a first invariant, and this is a second invariant, and this is third invariant. Third invariant. So that means this value, it won't change when I change to Planck system. Okay? If you use the Planck system value, add together, you'll get the same value. So this value won't change. That's called invariant. It won't change with respect to change the coordinate system. Okay? So that's called invariant. Yeah. All right. And this equation we call the characteristic equation, right? Characteristic equation, yeah. Okay, so here, this is very important. Why? Usually we do eigenvalue problem with directly. Some people just directly do this, but they don't know why. So this is coming from for non-zero solution. We have to require the B inverse to be singular. So that's why we require determinant to be 0. Okay? Yeah, that's the main reason. So this can be a qualified, PhD qualified oral exam problem. Tell me why. When you do the eigenvalue problem, you set a determinant equal to 0. Why? That's why. Okay. You just know it, but you don't know why. Okay? It's not right. No. As a PhD, as a professor, you should know why. Okay? Yeah. All right. So this is what I want to say to you. Okay? So once you determine the eigenvalue, then you can go back here, go back to this equation to determine the eigenvector. Okay, so for each lambda I, you have eigenvector, maybe something eigenvector I. Okay. Okay. So we call it eigenpair. Each eigenvalue with a corresponding eigenvector. So we call this eigenpair. Eigenpair. Okay. Oh. So that's what we call eigenvalue analysis. So buckling load, principal value, natural frequency, vibration mode, natural mode. Okay. So for buckling problem, there's a buckling load. There's a buckling mode. Okay. for principal value, principal value, stress, principal direction, natural frequency, mode, natural mode 1, mode 2, mode 3. Okay? So that's so important. Eigenvalue problem is so important in mechanics. All right? Yeah. Okay, so this is the first thing I want to tell you today. And I won't go to detail for the principal direction, principal vector, those things. Yeah. So sometimes you have a double root, okay, triple root. Okay, what that mean? Okay. Yeah. And sometimes you have a compressed number solution, the value, yeah, compressed number. Yeah. All right, and today I will introduce the Cartesian tensor field. I will show you the stock theory, Gauss gradient theory by tensor. Okay, so let's see the Cartesian tensor field. Okay, field theory. Field means in the spatial domain. Okay, for example, this is for example, this solid, and this is in Cartesian coordinate system. Okay, for x1, x2, x3, and this is a position vector. Position vector is a point P, and this is a position vector. So in mechanics, so this is a field. Maybe this is under loading. Okay, so we have a stress field. Okay, maybe with time, this position. At this position, at this time, we have a stress at this point. Okay. Maybe we have a displacement at this point, at this time, we have a displacement, maybe it's a displacement. Displacement vector, right? Because for next, this is a time t. Next time you move to here. The point P will move to P prime. So this position vector, it will have moved to the new position we call the if I use A, okay, position A, and this is a current, use X, okay, and this is a displacement vector, okay, and maybe we have a loading, and it's at time t, it will have this point have a stress. We also can have a strain at this point, the strain field. The strain tensor, this stress tensor, this is a displacement vector. Okay, vector is a tensor of order 1, right? Stress is a tensor of order 2. Maybe I have one temperature. is a T. At this point, at this time, it has a temperature. This is a scalar. Okay? Temperature is a scalar, not a vector. Okay? So you have a scalar valued tensor field. This is a vector valued tensor field. This is maybe tensor value, second order tensor valued. Okay, its value is a second order tensor. Its value is a first order tensor. Its value is a zero order tensor, scalar. Okay? So this is called the field. Okay? Field. So field theory is very fundamental in the mechanics description. Okay? Right? So all the strength field, stress theory are derived from this kind of displacement field theory. Okay? Yeah. All right. So when we do the mechanics, sometimes we will have